Molecular shape and polarity. So the polarity of a molecule has a big impact on the physical and chemical properties of the molecule. We talked about polar bonds, right? So we looked at hydrogen, I think we looked at hydrogen and fluorine, but hydrogen and chlorine would also be a polar bond because chlorine is more attractive to the electrons in that bond, it's more electronegative, and so they don't share those electrons equally. So if we looked at the electron density, we'd see that there's more electron density around the chlorine than around the hydrogen, and this end of the molecule is going to be slightly negative, the other end is slightly positive. So a diatomic molecule, two atoms, there's only one bond. If the bond is polar, the molecule's polar. In a polyatomic molecule, you can have a nonpolar molecule even though the bonds are polar. It has to do with how the dipole moments of those bonds add up. So the dipole moment is a vector. A vector, think of an arrow, and the length of it is its magnitude, and the direction is the position. And so it depends on what direction those vectors are pointing in. So let's look at carbon dioxide. So carbon dioxide has two carbon-oxygen bonds. Those bonds are polar, right? Oxygen's more electronegative than carbon, and so oxygen is pulling electron density away from the carbon. The other oxygen is pulling electron density away from the carbon on the other side. But the overall effect is zero. Overall, there's not one end that's more positive than the other or more negative. I think of this as people playing tug-of-war. Or here you've got, no, we'll just stick with tug-of-war. So here, this would be like the red flag in the center of the rope. And you've got big, strong oxygen over here pulling this way, and equally big, strong oxygen over there pulling the opposite direction. If they're pulling against each other with equal strength, is that flag going to move at all? Nope. We have a vector going this way and a vector going that way. When you add them together, because they're equal in magnitude, they add up to zero. They cancel out. So that's a nonpolar molecule. So vector quantities, the direction is always going to point towards the more electronegative atom. The magnitude is proportional to the electronegativity difference between the bonding atoms. We're not going to worry too much about the magnitude, but the direction will have a big effect. Any questions yet? Let's look at water. Water has two polar bonds also. Hydrogen and oxygen, hydrogen and oxygen. Here the bonds are the magnitude, the direction is pointing towards the oxygen because it's more electronegative. When we take these two vectors and add them together, they don't add up to zero. If you think about playing tug-of-war, here's big, strong oxygen playing tug-of-war with two little kids, and they're pulling him, in angled directions, and he's just backing up, pulling both of them, right? So the net effect, the net movement, is just straight up this way. The oxygen end of the molecule is going to be slightly negative. The hydrogen end is going to be slightly positive. So water is polar. And the shape matters, because if it was linear, it would be nonpolar. And that was one of the big clues about that led to things like VSEPR theory, is why is water polar? How are those atoms arranged?
Well, he's got those two.
Got the lone pairs. They didn't know about lone pairs, though, because they didn't know about electrons. And these guys were overcoming some big deficits in understanding. Okay, so how do we figure out if something's polar? You got to draw the Lewis structure, figure out the molecular geometry. Then you need to see, are there polar bonds? If all the bonds are nonpolar, the molecule's nonpolar. And then you'd indicate the polar bonds with vectors pointing towards the more electronegative atoms. The length would be proportional to the difference in the electronegativity. Then you figure out, well, if I add those together, is it going to make a net dipole moment? If the vectors add to zero, it's nonpolar. If they do not add to zero, then the molecule's polar. So let's just quickly review vector addition. Do you remember ever doing vector addition?
Oh.
Some people do. Some people are like, vector? What's that? Okay, on one dimension, it's easier to understand. So we're adding these two vectors, two arrows. We just say one side's positive, one side's negative. So this is positive on the right and negative on the left. So then both of these are positive. They're going to add together, and the net result is plus 10. The arrow gets bigger. In this example, we've got one going in the negative direction and one going in the positive direction, but the one going in the positive direction is stronger, is longer. And so when these add, they add to plus 5. It's the same as adding positive and negative numbers, which some people also have trouble with. Here we have a negative 5 and a positive 5. They're equal in strength, opposite in direction. This is the guy playing tug of war with another guy who's just as strong. Adds up to 0, nothing happens. Everybody okay with that? In 2 dimensions, what you do is you put those vectors with the same starting point, and then you draw a parallelogram. So from the end of this vector, I'm going to draw a line that's parallel with the other vector. I'm going to draw a line like that, and then I'm going to complete the parallelogram. This line is parallel to that line. The sum of the two vectors is this red line from corner to corner of the parallelogram. Here's another example. We've got this one and this one. We imagine a parallelogram, and the sum of these is this red one. It's really awesome if you understand vector addition. If you don't understand vector addition, you can still be okay in this class. So just hang on. Don't give up yet. What if you have 3 or more vectors that you're adding? You add 2 at a time. So for A, B, and C here, you add A and B, and you get R. And then you add R to C, and you get R prime. You can't do 3 at a time. You just do 2, and then add another. If you had another, you'd add that. Here we've got, this looks like a trigonal planar kind of a guy, doesn't it? That might happen with a trigonal planar molecule. Well, add these 2 first, you get this one. Add that one to this one, and the net result is 0. You got 3 people playing tug of war. You got 3 ropes coming from a central position, and they're spread out equally. They're equally strong. The rope's not going to move. Does it make sense? So here's a table which may or may not be helpful to you. You can read. Okay, so all of that was the real thing. Here's the shortcut. It is important to be able to tell, is a molecule polar or not. So this is the shortcut.
Are we going to need to do vector addition for the test?
No, I'm not going to make you add vectors. That was just an explanation of why this works. This is kind of the bottom line. So a molecule is nonpolar if both of these conditions are true. No lone pairs on the central atom, and all the atoms that are bonded to the central atom are either the same, or at least they have the same electronegativity. The no lone pairs means that all those polar bonds are distributed evenly around the central atom. So when we have pulling on electrons, it's going to be symmetrical. The atoms being the same or having the same electronegativity would mean that the vectors have equal magnitude, and so they could add up to 0. If one of these is not true, the molecule is going to be polar.
This is a lot easier to understand.
Right? See, I showed you the icky part, and then I saved the good stuff for last so you could appreciate it. Okay, so let's apply this.
Quick question.
Yes?
So what about when you have molecules like this? Like,
Okay, so that's a good question.
It's complicated to be non-polar?
Yes, they can.
Okay.
So And we find that in organic chemistry a lot.
But not in M1A?
Well, I'm not going to make you do those, but we can do them. So the thing about carbon and hydrogen is that the difference in electronegativity between them is only 0.4. So that's just at the edge between polar and nonpolar. And so it's considered a nonpolar bond. So if you say, well, all the carbon-hydrogen bonds are nonpolar, then you don't have to look at any of those. Then for like that molecule, you're looking at oxygen and nitrogen. Oxygen and nitrogen almost always have a lone pair on them. And they're going to form polar bonds with things like carbon and hydrogen. And so those are frequently going to be polar if they've got oxygen or nitrogen. And that'll be a big deal in OChem, understanding how that works, because that has a huge effect on the properties. Good question. So let's do CF4, carbon tetrafluoride. What do we have to do first? Draw a Lewis structure. So the Lewis structure is going to look like this. I'll spare you all the counting by 2. Okay, there's our Lewis structure. We're going to use my shortcut. Are there any lone pairs on the central atom?
Nope.
Nope. Are all the atoms bonded to the central atom the same?
Yep.
Yeah. So, what is it? Nonpolar. This makes a tetrahedron shape in which those polar bonds are arranged at 109.5 degree angles. Because these all have the same electronegativity, the magnitudes of those vectors are all the same, and they're going to add up to 0. What if this wasn't fluorine? What if it was chlorine? Now it's going to be polar. It still has no lone pairs, but because chlorine is different than fluorine, it has a different electronegativity. This vector is not going to add to 0 with the other 3. There's going to be a slight net dipole moment.
So would, okay, but so the electron geometry will be the same?
The electron geometry will be the same. The molecular geometry will be the same.
Change the angle? The chlorine?
Yeah.
That's a good question. Would it change the angle? Slightly. Chlorine's a larger atom than fluorine, and so these guys would probably be squeezed together.
Okay,
It'd be less noticeable than with a lone pair, though. It'd be very minor.
Chlorine's electronegativity have anything to do with that? Or,
No, that would have to do with the net dipole moment and the magnitude of the net dipole moment, the direction of it, because these are more electronegative. The dipole moment's going to point over towards the fluorines. The chlorine end is going to be the slightly positive. So polar molecules and nonpolar molecules have very different properties. You probably know from life experience that oil and water don't mix, right? Italian salad dressing, you shake it up and you set it down. You just watch the oil float to the top and the water, vinegar stuff goes to the bottom. It doesn't matter how long you shake it, it's still going to separate. And that's because polar and nonpolar molecules interact with each other in different ways. So polar molecules are a lot like magnets. They're not magnetic, but it's the electric version of magnets. So there's a positive charge and a negative charge, and they're attracted to each other, like the north and south poles of magnets. So here's a picture. We've got regular glass marbles, and these solid-colored marbles are magnetic marbles. I'd like to get some of these one of these days. But you can imagine what happens. The magnetic marbles clump together. And if there are any glass marbles in there, what happens to them? They just get pushed out. And that's exactly what's happening between oil and water. The water molecules are attracted to each other quite strongly. They're not attracted to the oil molecules, and the oil molecules aren't particularly attracted to each other either. And so they just get pushed out. So it's the water clumping together and pushing the oil out. The oil floats instead of sinks because it's less dense. Any questions?
So what would be, what's an example of something that would be non-polar but more dense than water?
Something that would be nonpolar but more dense would be like methylene chloride is more dense, and so it'll form a layer with water, but the methylene chloride's in the bottom instead. Yeah, it is.
So you can do methylene chloride, water.
Yeah, you can set up a really cool gradient. It's actually one of the really cool science experiments I remember from grade school. With these kits that came in, and we did this one, and we made these layers. I think they were different colored salt solutions or something, but it was really cool. We just, it was awesome.
I remember that vaguely. I have no idea it did not stick at all. I just remember the colors in the glass.
Yeah, very, very cool. Okay, so what do you do if you get oil or Crisco or butter on your fingers? You can't just rinse it off with water, can you? It just stays, right? Sugar rinses off real nice with just water. Grease, oil, not so much. Because it doesn't mix with the water. So I'm going to tell you how soap works. In case you didn't know, there's a picture of soap. This is what a soap molecule looks like. It has one end that's polar. It's got some oxygens here. And so this end is polar, but the rest of this is all carbons and hydrogens. Nonpolar bonds, very symmetrical. This nonpolar tail. Well, this nonpolar tail is a lot like the oil or the grease. And so this mixes well with the grease. The polar head, it interacts with the water. And so what happens is it makes what are called micelles. And I'm not being possessive there. M-I-C-E-L-L-E. I dare you to draw a micelle while spelling micelle. Okay. So here are the polar heads. Those are going to be on the outside. It's kind of like circling the wagons. And here are the tails, and they're in this little glob of grease. And because it's got these polar heads on the outside, it's like, sneaking somebody out or sneaking somebody in, and let's stand around, and so nobody will notice who's behind us. And so the little grease globs can get washed away by the water instead of just clumping together and staying on your hands. So soap.